carrying on with our kind of assessment of data as it relates to normality and just an introduction to Stata, we just described that we can do histograms with a lot of different variables just by typing in histogram or clicking on a previous command of histogram, and then we can then type in or click on a different variable. We may want to do a histogram on something like household income, and we can see here's our histogram of household income. See this long right-handed tail for household income. Doesn't kind of see the bell there, but then this huge tail kind of takes away from the normal aspect of that bell curve. If we were interested in seeing how well it fits along the line, you can also use the command qnorm, and I can type in qnorm and then click on our variable for household income, and you can see this huge departure away from the line of best fit. Our data clearly do not fit a normal distribution, and somebody may want to not use that type of data analysis for income data, where a lot of stats, as we will discuss, a lot of statistical tests assume normality. Some folks will try to straighten the data out by doing what is called log transforming the data, which we can start toying around with log transforming data here in a minute, where I'll teach you how to generate a new variable that may be a categorical or a income-based category, or whatever category we want to create. So we can do that here in a few minutes. Now, if we want to actually make a decision or a determination of whether or not our data fit the normal distribution, we can use a p-value based approach to determine how confident we are that our data do or do not fit a normal distribution. Now, the two types of normality tests that exist in Stata are the Shapiro-Wilk and the Shapiro, I think it's Francia, and those are the two types. Some other programs will have what's called the Anderson-Darling test. It's named after these various statisticians. If you were to do a Google search on Stata normality test, you might find a document that looks something like this. It will tell you that the Shapiro-Wilk test, the command for it is swilk, and the other test, the Shapiro-Francia W test, it has a command that is that, sFrancia. It gives you some examples of how you can actually perform it. You can do it on multiple variables at the same time, and it tells you a little bit more information about these particular tests. It tells you that Shapiro-Wilk tests are good for 4 to 2,000 observations. sFrancia tests are good for 5 to 5,000 observation tests. And then if you need even more tests, they have another one called the SK test, which we can click on to learn more about. The SK test requires at least 8 variables and then goes up a lot higher. But we'll go back to just doing the sFrancia test because we've got between 4 and 5 or 5 and 5,000 observations. So the command from that program, if we were to do Shapiro-Wilk, let's see what it does for something like household income. It may flag it. Okay, so it still ran the test. and it says that our p-value, and this is our p-value, this probability is greater than z or whatever, our p-value here, this is the same thing as our p-value from our previous information, previous notes. But it does tell us that this is not good for 4 to 2,000. We have 3,134 observations. That's more than 2,000. But if we were to use it, we have a p-value of 0.00000. That is way below 0.05. So there is a statistically significant difference between these data, the household income data, and what a normal distribution for this many observations would look like with that average. If we were to do the other test, the S-Francia test, which is more appropriate since we have between 5 and 5,000 observations, we still see a p-value well below 0.05. So again, we are quite confident that our data for household income do not fit the normal distribution. So we would then conclude that our data are not normally distributed, and the word for that is non-parametric. So you might see on the statistics, non-parametric test. These are types of statistical analyses for data that do not fit the normal distribution. We may be interested in doing this same type of test on a variable like life expectancy. So we'll do the Shapiro-Francia test on life expectancy and see how it does. And again, it also does not perform normally. Our data are skewed, and that is not all too uncommon. Whenever you're dealing with social science data or dealing with environmental health data, in many cases, our data in non-laboratory based studies and studies that are examining human nature, we see these dramatic departures from the normal distribution. So don't be alarmed. People still use normal statistical tests for data that don't fit the normal distribution. They may not want to, but they still do. Now, there are some folks that want to try to straighten these things out. Like, can we make household income fit our Q norm? Can they fit that plot a little bit better? So we'll go up to median household income. Again, I've got it saved on here somewhere. If I can find where it went. Household income. So can we make the data better fit this line, or at least get closer? And one way that people may do that, it doesn't change the actual data in terms of their order or rank, and it still maintains the initial quality of the data, but it does kind of transform the data onto a log scale. So some people may generate the data as log data. So we may generate a new variable called generate. That's the command, generate. We'll call it log10 income. And that equals our variable household income. But we're going to say log 10 of the household income. And so we created a formula saying create a variable called log10 income equals that variable household income on a log10 scale. Let's see if it works. All right, so it generated one missing value. We could explore that further if you wanted to. So we're here in edit mode. I just generated a variable, and there it is, log10 income. One of the values, somewhere in there, it may have been missing or something. It didn't generate one for it. So there's our log10 income. So I'm going to then hit summary just so you can see what we've got, log10 income. And our average income now is 4.67. So the average income display equals 10 to the 4.673912 power. That's our average income, 10 to that power, because that's the log number right there. So the average income for the United States is $47,196.74 on that log 10 scale. If we were to do the original variable household income, what do we have? 48,591. So it didn't change it all too much. What about the medians? The median should stay the same. The order should still be the same. The median income is 4.67. The mean is 4.67. So if I were to hit display, and then we'll say 10 to the median, which is 4.670125. We'll do that. We got 46,786. What's our median household income for the United States? So we'll type in household income, 46787. So these are essentially the same exact numbers. The ranks did not change. How does our log data, our Q-norm data, look on that graph now? It straightened it out a whole lot, didn't it? So we got it closer to behaving as normal. It still may not pass the normality test, but it sure as heck looks a lot closer to being normal. If we wanted to compare that with what we remember was this one, household income, you can visually see what the log transformation did. It smoothed it out and made it behave a little closer to normal. If we wanted to do a histogram and look at those bar charts, we can do a histogram on log 10 income and see something closer to a bell curve, maybe. That's what we currently have. What did we have before? It didn't look pretty, that's for sure. So a huge right tail. So we straightened it out a little bit. We can then we can scroll up to that command S Francia. I can change the variable name to log 10 income and run it and see what happens. Do we pass the normality test? We tried to straighten it out by log transforming it, and we still fail to meet the normal distribution. The data are still significantly different from normality, and that sometimes happens. So later on, as we go into the class, we will discuss how certain statistical tests expect us to use normal statistics or non-parametric statistics. Right now, these data suggest that we should probably be using non-parametric statistics. And in some disciplines, I've heard that political scientists, they often use non-parametric or non-normal statistics all the time. And other disciplines just totally disregard everything that we're covering here and use normal statistics even when the normal assumption is not met. So what we've covered here in this section, and you can copy and paste all this, these commands. You can right click it and paste it into Microsoft Word. If you wanted to do that, you can create a new document. When you paste information in the Word, it looks ugly, but if you were to change it to Courier font and make it small, like a size 8 or 9, now it suddenly looks just like what you had for your output. So that's a little bit about histograms and normality testing in Stata. We're going to have a couple more videos for this first section on how to use the software to look at data. So thank you.